All right, good afternoon, everyone. Just a couple of reminders. We do have an SI session tonight. All right, so if you want to go to that, if you can make that. Let's turn this down a little. And remember, we have our exam coming up in a week and a half. And so we still have time for that. So we're going to be finishing off chapter 18 and doing chapter 19 as well. So there will be chapters, what is it, 16? No, it's 16 through 19. All right, okay, let's quiet down. Okay, yesterday we started to talk about what happens when we put a substituent on a benzene ring and we want to do another electrophilic substitution reaction. All right, we talked about the different groups that we could, that we've covered, and we placed them in terms of being activating and deactivating. Okay, so in general sense, what do activating groups do as far as electron density? Do they donate electron density or withdraw electron density? They donate electron density, right? Okay, let's quiet down, please. So these are electron donating, and deactivating groups do just the opposite. So these are electron withdrawing. And we can understand this difference just by thinking about the role of the benzene ring, which is to be a nucleophile, right? So the more electron density there is in the ring, the more nucleophilic it will be. We started in after that talking about the next stage of this, and that has to do with directing effects, okay? And we looked at a methoxy group, which is an activating group, and we went through a big analysis to see that the methoxy group is also what we call an ortho-para-directing group. Yeah. Oh, interesting. Okay, here, let me try something different. Okay, so activating group was also an ortho-para directing group. All right? And I'll just show you that whole slide again in just a moment. And so what we're going to do next is we are going to look at a deactivating group and see what it does as far as directing. All right? So our goal is to then, if we understand activating, deactivating, and directing, then we can start to synthesize benzene rings that have multiple substituents on them and control what positions they go to. All right? Once we've done that, I don't know if we'll make it through all this today, then there's a couple other reactions that are called nucleophilic aromatic substitution reactions, right? So far we've only looked at electrophilic substitution. So these will be reversed, and so the benzene ring will act as the electrophile rather than the nucleophile. That sounds pretty exciting. All right, let's do a clicker.
No partial charge on D? I thought there might be, but...
All right, so this is where we finished off yesterday. It was this big slide. And so what we essentially did was go through and place our chlorine on the ortho, the meta, and the para positions, and then analyze the resonance stabilized carbocation that would form. All right? And what we found through this whole analysis is that when we place that chlorine in the ortho position, we end up with an additional resonance structure. as well as when we put it in the para position, we end up with this extra resonance structure. We don't have that when we place the chlorine at the meta position. There's no way to move the charge from the ring out onto that methoxy group. And so ortho and para are favored for this activating electron donating group. All right? And so this is going to be true for all of the electron donating groups. Okay? Sorry. All right, so the next thing we need to do is look at what happens if we have an electron withdrawing group. Okay? And so we have to go through this whole process again. And so what we're going to do is we're going to add that chlorine to the ortho, meta, and para. I probably won't draw out all of the resonance structures this time, just enough to be able to see what's going on. Okay, so the first one, we're going to add the chlorine to the ortho position. Okay, so we're going to put a chlorine up here. Oops, come on. Here's our nitro. And I'm going to draw out the Lewis structure for the nitro, which shows us that we have that plus charge on the nitrogen. And then we have, let's see, what did I do wrong here? That, yeah, this double bond, and this is going to put a plus, right? That's kind of a sloppy drawing. But the plus right where the nitro group is. Okay? Like we did before, we can, let's just draw one more. We could move this pi bond toward the plus. Which would shift to here. If I can get close enough there. And yes, I am recording. The one thing I'm doing right this time. All right, so there's the other one. So the important resonance structure here we've already drawn, and it's the one that has the plus right attached or located on the carbon that's bearing the nitro group. Okay, that's going to be the least stable because we have the plus right there. We're trying to milk this, whatever, this stone or whatever the saying is, right? We're trying to get electron density out of that carbon that already has a plus. Okay, so this is very unstable. Okay, so let's look at what happens if we put it in the meta position. Okay, so now we're going to put the H here and the chlorine there, and the plus ends up over here. All right, so now we're going to draw the other resonances. So we move that pair of electrons over. And we get the plus right here. Like that, right? And then let's do it one more time. All right, so this pair can move over here, and we get one more. And these are just the three normal resonance structures that we get whenever we do this electrophilic substitution reaction. That moves it to here. There, here, and here. All right? So, does the plus ever end up on the carbon that bears the nitro group? No, it doesn't. Okay, so let's look at our last possibility. We're going to put that chlorine in the para position. Right, that's on the opposite side of the ring. So we will put the H and the chlorine over here. We have a double bond there, double bond here, and a plus like this. All right, let's draw a resonance form. We'll bump those electrons over toward the plus. That puts a plus right there. Okay, so notice in this case as well, the plus gets spread right to the carbon that bears the nitro group. And so in this case, for the electron withdrawing groups, it's not that we're going to look at specific resonance forms and say, oh, that one's super stable. In this case, we're looking at these two examples are the least, well, the meta one in the middle is the least bad. All right? Because all of these are going to be somewhat destabilized because we're pulling electron density away from a carbocation. All right? But the examples where we have the nitro group right where the plus is are even worse. Okay? So this is like the worst here, the least stable, as is this. Okay? So the meta position is the least bad. All right? And so an electron withdrawing group like this will be a meta director. Okay? So we have a deactivating is going to be meta directing. Okay? Just because that's the best it can possibly do, even though out of some bad choices. Yes?
Just a quick question. In the book, it lists the halogens as deactivating as well, but it also says that they are orthopara directors?
Correct.
Okay.
Yeah, let's look at the table and I'll bring that up.
Okay.
Okay, so the next table of all of the substituents that we looked at before. Right, so before, remember, we drew our line right here. And they were activating groups above that line, deactivating groups below it. Okay? When we look at orthopara directors, we notice that all of the activating groups are included in that, but so is the halogens. Okay, so they're again kind of the oddballs here. So the halogens are deactivating but they are orthopara directing. Okay, so they are the unusual one in here. Okay, other than that, all of the deactivating groups are going to be meta directors, and all of the activating groups will be orthopara directing. Okay, it's these halogens which are unique to this whole thing, and they just sit right on the borderline. Okay? All right, so let's look at a few examples here. So we're going to compare the ratio of products if we have alkyl groups. Okay, so alkyl groups, we didn't draw those out, but alkyl groups we talked about as being weakly electron donating groups, and so those are going to stabilize the carbocation, and it's going to stabilize it the best when the carbocation is right where the alkyl group is. Okay? And so they are I'm going to just do it like this, orthopara directing. Okay? So if we put a methyl group, so if we start out with toluene, and we do a bromination reaction, okay, we can get a mixture of para and ortho products. Okay? We have 2 possible ortho positions and only 1 possible para position. right? So if we think back to when we were looking at statistics, when we were talking about radical reactions, we might think that we should get more, slightly more, well, maybe twice as much of the ortho versus para, okay? And in fact, we don't get quite that, but we get a 2 to 3 ratio, okay? So we do get slightly more ortho than para because there's twice as many positions that it can go to, okay? If we go to an ethyl group, then what do you think is going to happen to the ratio? Is it going to change at all? Is an ethyl group any different, as do you think, or very much different as far as an electron donating group than a methyl group is? I don't know, maybe not that much different, right? What else could play a role?
Like, it being bulkier, it's going to push away the bromide.
Exactly. So it's not so much the electron donating here, but it's that ethyl group is bigger than the methyl group. All right? So there's going to be some steric strain when trying to have the bromine attack at the position ortho to the ethyl group. Okay? And so now we go from 2 to 3 to 1 to 1. Okay? So it still favors the, well, it's starting to favor para, given that there's only half the number of para positions as ortho. All right, if we go all the way to the tert-butyl, then that's getting really very much bigger, and so then we go to a 4 to 1 ratio. Okay, so we still see some ortho, but we're starting to favor the para. Okay, so usually if we're doing a synthesis, if we have a choice, if we can use a bulkier alkyl group and we want para, then we can drive it para a little bit more. Okay, otherwise, ortho-para directors, we're often going to get a mixture. So if we're doing a synthesis, we may have to say, oh, we're going to get ortho and para products, we're going to have to separate them, and we'll move forward with the one that we want. Okay, so it could be one product. All right, so there's a couple of further things to think about. So if we have phenol with this OH right here, what type of a group was that? Activating or deactivating? Activating. Activating. And so what kind of directing? Ortho-para. All right? And in fact, an OH is a strong activating group, and so if we use our normal conditions of bromine with our catalyst, then we end up essentially getting bromines at all of the ortho and para positions. Okay, it's just so reactive. Okay, and so with a strong activating group like an OH, we can actually get away with having no catalyst if we want to put in on a single bromine. So then we're going to get a mixture of the ortho-bromophenol and the para-bromophenol. Okay, so when we have a strongly activating group, we don't need the catalyst. Yeah?
What other groups would you consider strong activating groups?
Yeah, I think the one, so good question. The question was, what other groups are strongly activating? I think the other one are the amines. So the O right there or a nitrogen, they're both good at donating electrons in that way. Okay? All right, so what if we want to do these two reactions? So this is the Friedel-Crafts alkylation, Friedel-Crafts acylation. These two reactions are, in fact, the least reactive of all of the reactions that we looked at. All right? And if we have here a strongly electron withdrawing group, then we get no reaction. Okay, and this is basically because the ring is so deactivated that it just won't react in the Friedel-Crafts reactions. Strongly deactivated ring will not do the Friedel-Crafts reactions. Okay, so this is kind of a limitation. And then there's one more, and that is that if we have an amine like aniline, and we try to do a Friedel-Crafts reaction, so let's say we have just, I'll just put CLR. Okay, this as well has no reaction. Okay, so why do you think, so is this because the ring is strongly deactivated? No, because this is one of the strongest activating groups. Okay, so what happens in this case is that the non-bonding electrons on the amine actually do a Lewis acid, Lewis base reaction with the catalyst. So these react with the aluminum, and they react more easily with aluminum than the chlorine alkyl chloride. And if we do that, let's draw out what we would get. We get this product of this Lewis acid, Lewis base reaction. We'd have the aluminum trichloride onto here. And what kind of charges would we have to put on this? Positive on the nitrogen, right? Negative on the aluminum. Okay, so now, if this is the species that's in solution now, is that nitrogen still going to be a strongly activating group? No, because now it has a full plus charge on it. So it turns it into a strongly deactivating group. Okay? And so just this combination doesn't work for the Friedel-Crafts alkylation or the acylation. Okay? So there's just these little limitations.
Professor,
Yes?
just quick with the bromine, if we have a strong activating group, we don't need a catalyst, but that's only to the monobromine, right?
That's if, yes, exactly. So for the strongly activating group, if we want to only monobrominate or chlorinate or put one nitro group or any of these things, then we can go without the catalyst.
But we need the catalyst in order to do the tribromine.
Yeah, if we want the tribromo compound, we'd have to use the catalyst. Yeah. Some reaction. So what we want to be able to do now is design some syntheses, okay, and come up with benzene and imagine how we could synthesize the molecule. So here we'll do these three. We want to devise a reaction sequence to synthesize the molecules from benzene. Okay, so maybe take a moment and think about what series of reactions you could use to make this metachloroethylbenzene. Right, and so when you're thinking about these, you're going to be thinking about, you know, what group to put on first and which one to go on second and whether they're going to direct the next group into the right place. And so let's just work this first one together. Let's look at the two groups we have on there and determine whether they are ortho, para, or meta-directing groups. right? So what about the chlorine? It's an ortho-para directing group, right? So if we put the chlorine on first and then try to put the ethyl group on, the ethyl group will go ortho and para, right? But we want it at the meta position, okay? What about the ethyl group? What kind of directing does it have? Ortho-para as well, right? So what do we do? Yeah.
You start with an acylation and then add the chlorine and then do the reduction.
Yes, excellent idea. So the idea is that we know that we can make this ethyl group from an acyl group, and the acyl group is a meta-director. Okay, so if we, let's do this in a retrosynthesis way, if we go back to having an acyl group here, right now this one is easier to make because we see that we have a meta-directing group on the ring. So if we put that meta-directing group on first, then we chlorinate, the chlorine will go to the meta position, and then we have to convert that acyl group into the alkyl group. Okay? So if we keep going backwards here, we would go back to just the acyl group. And then back to benzene. Right, so the first reaction is the Friedel-Crafts acylation. Right, we just want to add an acetate group there. So we use acetyl chloride and aluminum trichloride. All right, it's just a standard Friedel-Crafts. Then we want to add a chlorine, and because that acyl group is meta-directing, the chlorine will go to the meta position. So we just use chlorine and iron 3 chloride. And then we need to convert the acyl group into the alkyl group, right? And we talked about a couple of ways to do that, right? We can either use hydrogen and palladium on carbon. Where's that one? No, we used the Clemenson and the and the Wolff-Kishner. That wasn't the right. So let's use the Wolff-Kishner. And hydroxide. Okay, so that takes off the oxygen of the acyl. Okay, so you have to think about what directing they can do. And oftentimes the trick will be that you have to put on one group and then the second one and then convert the other one into something else that kind of, hides what it was able to do. All right, so let's look at the one in the middle. All right, so what about the directing of those two groups? We have a methyl and an isopropyl. Right, so they're both ortho-para directing. And we want them to be para, so that's okay then, okay? So the question is, we can put one of those on, we put one alkyl group on, and then it's ortho-para directing. We'll get a mixture, but some of it will be the para, and that's the one we want. So is there one of these groups that we should put on first if we want to maximize the amount of para directing? Right, put on the isopropyl group first, right, because it's bigger, and that will give us a better ratio of para to ortho. Okay, so if we go back one, we'll go back to this with the isopropyl, and then from there back to benzene. So all we're going to do is 2 Friedel-Crafts alkylation. Okay, so we do this with, well, we can use 2-chloropropane, or we can use 1-chloropropane, right? We saw that we get a hydride shift in that case, right? And so this is bulky, right? So it's going to drive it to the para position. And then the second one, we're just going to use methyl chloride and aluminum trichloride. All right? Okay, what about the bottom one? Okay, bromine is orthopara, and the amine also orthopara, right? So we're kind of in a situation like we were on the first example. So can one of those groups come from a meta-directing group? Right, the amine we can make from a nitro group, okay? And the nitro group is the meta-director. So if we go back one, we convert the amine, if we're going backwards, into a nitro group. Right? And the nitro group is meta-directing. Okay, and so then we go back just to the nitro and back to benzene. Right, so our first step is just going to be the nitration reaction, HNO3 and H2SO4, nitration. Then we need to do the bromination. The nitro group is meta-directing, so the bromine will go meta to the nitro group. Br2, FeBr3. And then we need to reduce the nitro group to the amine. And this is where we use the hydrogen and palladium on carbon, or the tin and hydrochloric acid. Okay? Any questions on that? All right, let's do a couple more. It's so fun. Everybody's falling asleep. All right, so what kind of a directing group? Well, we already talked about the nitro group, right? Meta-directing, right? What about that carboxylic acid? Should be meta-directing as well. All right, so now we have 2 meta-directing groups, but we want those groups to be para. No, we can't go from the amine back to the nitro group. We can only go from the nitro to the amine. Yeah?
oxidize that using the CHEM approach?
We could. So the suggestion is that we can make this carboxylic acid by that benzylic oxidation. All right, so we can start with an alkyl group, or we can put an alkyl group on there, which is an ortho-para director, and then add the nitro group, and then convert the alkyl group to the carboxylic acid. Okay, so if we go backwards here, we're going to have to go back first to an alkyl group at that para position. All right, so we could pick any alkyl group we want as long as that alkyl group has a hydrogen at the benzylic position. Right, so any choices, anything that would be better than anything else? Yeah, isopropyl would be good because we want to drive as much para as we can. So it's kind of better to make a bulky group here. You know, we could do it with methyl, but we'd get more like a 1-to-1 or 2-to-3 product. Okay, so we can go back to that. Then the alkyl group is ortho-para directing. So we'll put on the nitro at that point, and then the very first step will be to put on the alkyl group. All right, so let's write these out in the forwards way. We do our Friedel-Crafts alkylation. Right, then we do our nitration. And then we do our benzylic oxidation, which was with potassium permanganate. All right? All right. One more, and then we'll just call it a day.
Now, I think you have an extra isopropyl on that first step, just for those who may be watching.
Oh, top right. Oh, you're right. This shouldn't be on there yet. Yep, thank you. Okay, and so this one we're going to have to do some chemistry on the side chain as well. Right, so let's just kind of work our way back. Okay, we need to have, we can't change the directing of the bromine, right? So we have to go through some functional group that is a meta-director. Okay, so what's that likely going to be? Yeah, the ketone or the acyl group. So at some point we need to go back to here. Okay, but then once we get to here, we need to be able to convert the ketone to this alkene. Okay, so let's go back. Let's just get the substitution right first. Oops, no, I don't want that on there yet. Go to here. And then back to benzene. Okay, these are similar steps to what we already did. Okay, so how do we convert that ketone here into this vinyl group over here? We could do a reduction. I don't think, we don't really have a way to do a reduction to an alcohol yet, I believe. That's a reaction we're going to learn. But we could reduce it all the way. If we reduce it all the way to the ethyl group, can we still get there? Yes. All right, so if we reduce this all the way, let's just do the same as we did before. Wolff-Kishner goes to, I think maybe we made this one already before. All right, so now how do we convert the ethyl group into the double bond? Yeah.
Did you do a radical reaction to brominate it and then do the elimination reaction?
Exactly right. So what we need to put a functional group on there. The only functional group we know to put on that benzylic position really is to brominate it. Okay, so let's use, let's say NBS and heat. All right, so that is going to do a benzylic bromination. Oh, wrong position. Here. Right, and then we need to do an elimination reaction. Right, so it's probably better to minimize substitution. We could use a bulky base like tert butoxide. Right, so it's just doing an E2 elimination. All right. Okay, so what if, since we got like 2 minutes left, what if we wanted to end up not at the double bond, but we wanted to end up with a triple bond over there? Yeah.
You can do the radical reaction and yes twice and then do elimination.
You might be able to do that. Well, we're starting with the double bond, though, now. Well, let's see. Well, yeah, we don't even have to start there. So the suggestion is, and this might work, is that if we did, I'm going to go back this way, the NBS with heat, if we could do this 2 times, and I'm not sure if I've seen that doing it. I don't know if there's any problem with putting the second one on that position. And then this is a bromine over here, and then we have to do a double elimination. So we could use NH2 minus, and we got to do this 2 times as well. Okay? So that's one possibility. All right, there's another way we could do it from the alkene, even though if that worked, it would be faster, right? Because we're going from that intermediate rather than going all the way back over to here and then down that way. So we could also just do an electrophilic bromination to the double bond. And that would put 2 bromines on. And then we do the same double elimination, right? So NH2 minus, and we do this 2 times. All right, does a double elimination to get to the alkyne. Right, and then we could deprotonate that thing, we could extend the chain, we could do all kinds of cool stuff. All right, so I will see you guys tomorrow.